All right, so this is VSEPR and molecular geometry. VSEPR, chemists call it VSEPR, but it stands for valence shell, electron pair, repulsion. So VSEPR, VSEPR, valence shell. Valence shell, those are the areas where the electrons are, the outermost electrons. Remember, valence electrons are the ones involved in bonding. They are in electron pairs, ladies, right? Either in a bond or they are a lone pair on an outer edge. And then electrons repulse each other. So if ever you've had food and it's repulsive, it's like, ugh, that's nasty. What you're doing is you want away from the food. Well, electrons repulse each other because they're both negatively charged. And that repulsion shapes the molecule. So why do we care about Lewis structures? So Lewis structures help us understand about this valence shell electron pair repulsion. So Lewis structures, number one, give us an idea of the skeletal shape. We can figure out what the skeletal shape of the molecule is. Skeletal shape. And from the skeletal shape of the molecule, we can figure out what's called the electron geometry. This is the number of electron clouds around a central atom. And then from the electron geometry, we can figure out the molecular geometry. And this will make a little bit more sense in a minute. What do I mean by electron geometry? And that will lead us to the molecular geometry. And finally, why the heck do we care about the molecular geometry? It's because it tells us solubility. Solubility. Solubility is an important physical property of many compounds. We need to know ahead of time if something's going to dissolve in something else. So it is really important for creating soda. The fact that carbon dioxide does not dissolve in water makes for fizzy soda drinks. It's also very important in our salad dressing. So if you look at vinegar and vinegar and oil separate, right? If you leave it on the counter for a little bit, you notice it separates. It does have something to do with the density, but it also has something to do with the fact that they repulse each other because they're not soluble in each other, which is why you take your salad dressing and shake it up before you pour it onto your salad. This same phenomena, salad dressing and soda are all important, I guess, but it's really important on a cellular structure. Do you guys, anybody remember the phospholipid bilayer of the cellular membrane? Right? You guys, maybe that's ringing a bell from biology, or you're like, what did you just say? Our cell's membrane is like vinegar and oil, and it is a phospholipid bilayer, meaning it's got fat and it's got not fat. And because of what it can dissolve and what it can't dissolve, that is literally the gateway of what is allowed in your cell and out of your cell. So all cellular function is actually dictated by solubility. So if you are a biochemist, which that was what my degree was in, you get to learn this in great detail, more so than you ever cared to. But it's very important when dealing with understanding maybe how a drug might affect a patient or why a disease might be affecting a patient a certain way. It could also be just merely being curious about the way living things work to better understand what's going on with cellular processes. Okay? It also might be important for maybe the engineering of an engine, the motor. I mean, we put motor oil in there. We need to make sure it's not dissolved by certain stuff. So engines are another aspect that this VSEPR theory is really important. So we're going to draw a little chart. This chart is going to have 3 columns. So the first thing we're going to show is the 3D model. The second thing we're going to show is the electron geometry. Electron geometry is determined by the number of electron clouds. Electron clouds, folks, there's really 2 types of electron clouds. There are atom pair bonds and those are our lines, right? When we draw our Lewis dot structure, they're the things that are lines, either a single bond, double bond. The second type of electron cloud would be a lone pair. We represent those with dots, right? The 2 little dots that are surrounding in our Lewis dot structure. So electron clouds are either a bond or a lone pair. They're either a line or dots when we're looking at the Lewis structure. The last thing is our molecular shape. Our molecular geometry, and that determines the shape. And the shape then can tell us whether something is soluble in something else. So it's important to understand the shape before we get into what's called intermolecular forces. So it's how 2 different molecules interact, or 2 of the same molecules interact. Because let's face it, in nature, nothing is in isolation. It's always with other things. So it's important to understand how it interacts with other things. All right, so the very first one is called linear. It looks like this. Here's the 3D model. It's a central atom with 2 things on either side, kind of like carbon dioxide. Yeah. This thing has 2 electron clouds. Actually, it's got 2 things bonded to it. Okay, 2 electron clouds. We call this linear. It has 2 electron clouds, yeah. And therefore, its electron geometry and its molecular geometry are identical. So it is also linear. All right, if this thing happens to be a binary, it's 2 things like this. Realize there are electron clouds outside, but if it's binary, it's an exception, and we call this thing linear. All other times, we do not. So if binary, ignore valence electrons. All right. Linear. Linear is a fancy word for a line. Do you guys agree that the red, black, red are in single file line? Yeah. In fact, if I'm looking at it like this head on, all I see is the red. They're all in alignment with each other. They're not out of line, they're not zigzagged. The next type of model is when you have a central atom with 1, 2, 3 things. Oh, I forgot to tell you what the bond angle is for this. What is the angle right here? What is an angle that's like this? 180. Good. What do you think the bond angle is there? Oops. What is a full circle? 360. So this is just 1/3 of it. 120. Yeah. So the bond angle there is 120. You guys are going to get to do a PhET simulation tomorrow and the next day that gets you playing around with bond angles. These are in theory, but in actuality, you'll see that they fluctuate just a little bit. And bond angles are kind of important for things interacting with other things. All right. The electron geometry for this is called trigonal planar. Trigonal planar. It has 3 electron clouds. This is an example of something that is trigonal planar. Plane. What does it mean to be in the same plane? Well, in my mind, if I take a knife and I chopped down this, I would touch each and every element. If I were to take a knife and chop down this, I would touch each and every element. It is in the same plane. That's what planar means. Trigonal, of course, means there's 3 things. Versus linear, it's just in a line. Okay? Now, if all 3 of the things, all 3 of the electron clouds are elements, the shape is the same exact name, trigonal planar. But what if one of these is not an element, but rather a lone pair? So you've got a little lone pair right here and 2 elements coming off. So there's 1, 2, 3 electron clouds, but one of them is a lone pair. What is this shape? It is bent. Hey, somebody have a lunch date? Abigail and who? And Natalie. So this is the shape. You've got the little lone pairs right there, and we call this bent. So electron geometry differs from molecular geometry. Electron geometry just, you say self, how many electron clouds are surrounding the central atom, and then you say, all right, are all 3 of them elements, or is one of them a lone pair? And then the last one, and I won't go much further than this, although the simulation will keep going, because I don't really want you to know too much further than this. You've got a central atom with 4 things coming off of it. The bond angle for this is 109.5 degrees. And what we call this thing right here, with 4 things around it, by the way, 109.5. So if I were to take a protractor, is that the thing that measures angles? Yeah, thanks. I forgot the tool name. Protractor. This is 109.5 versus this is 120. And you can kind of see how that one's closer, right? Like if I align these up perfectly, you can see the white to black is a little bit closer angle than the red. So this is 120 degrees, this is 109.5. No matter which way I turn it, it is always 109.5. Remember, these little things are repelling each other and they want to be as far away as possible. Nature has figured out if I'm 109.5 degrees away from you and you and you, that's the prime location. If I move a little bit closer here to be farther from here, well then I'm too close to this guy, right? Because these things are repulsing each other. We call this a very fancy word. It's called tetrahedral. This means there are 4 electron clouds. If in fact all 4 of the elements are the things that are in the electron cloud like this, call it the same thing. Its shape is tetrahedral. But if one of them, here I'm going to pop this thing off, if one of them is a pair. Do you see how this is different? Is this in the same plane? If I were to take a knife and chop through it, would I hit everything? No, it's not planar like how this one is. This one is planar. They are all in the same plane. This one's called trigonal pyramidal. It's almost like a pyramid. If you put it on a flat surface, the black one is not touching the three white are. So it's uplifted just a tad. So if it looks like this, it's got one lone pair, it's trigonal, pyramidal. And then the last one, like water, for example, is this. If I have two sets of lone pairs, so I have lone pair, and two elements coming off, this is also called bent. So the tetrahedral has three different possible shapes that it could be. So I'm going to go through two examples really quick if I have time, hopefully, and show you what I mean. We've done CO2 before, but let's do it again. Abby? What are the lone pairs? Those are electron pairs that are not shared between two elements. They're just there. They are valence electrons, and they're there in order to achieve octet. So look at CO2. Let's do CO2, and I'll show you what I mean by lone pairs. Yeah, I think like 5 minutes. Does that mean right now? Yeah. Because we get out of here at 29, right? Mm-hmm. Yeah. So CO2, carbon has 4 valence electrons. Oxygen has 6, but there's 2 of them. This means we have a grand total of 16 valence electrons total. Carbon would be the central atom. We'd make our skeletal structure. Those lines right there at what Abigail was asking, those are no longer lone pairs. They're shared electrons. And they represent 2, 4 electrons, so we've got 12 left. And remember, we distribute first to the outer edge, our outer terminal atoms. And this doesn't work. Those lone pairs right there are great for oxygen, but carbon is not happy. It has not achieved octet, so remember it says, hey, carbon, we'll share these. So the actual structure is this. So if I look at that central atom, how many electron clouds are coming off of it? I've got 1, even though it's a double bond, 2 electron clouds. Those electron clouds, since there's 2, bye, have a good afternoon. It is now considered a linear, both electron geometry and molecular geometry. We would call it linear. It's both. The other example I want to give you is water. So we do a valence electron inventory first so we can draw our Lewis dot structure. We've got 2 hydrogens, each with 1 valence electron. Oxygen has 6, so we've got a total of 8 valence electrons we have to deal with. We have oxygen as our central atom. So we've dealt with 4. We got 4 electrons left. Hydrogen has achieved duet. Remember, hydrogen's the exception. It doesn't want to achieve octet. So we're going to take those 4 remaining electrons and put them on the central atom. That way oxygen has achieved octet. Now, as far as the electron clouds, yeah, here's 1 electron cloud, another electron cloud, a 3rd electron cloud, and a 4th electron cloud. So because of that, its electron geometry is considered tetrahedral. But because two of them are lone pairs, its molecular geometry is bent. So this is water, this is carbon dioxide. Carbon dioxide is linear, water is bent. This has something to do with the solubility, and we'll learn more about that later. Perfect timing.